Yeah, it's recording now. Uh, Gain margin and phase margin. So today topic is related to gain margin and phase margin. Now, in the last lecture, we discussed about Bode stability, and we said that Bode stability says that for phi equal to minus 180, whatever the crossover frequency we have, corresponding to this crossover frequency, the amplitude ratio should be
One.
should be
One.
less than 1 for system to be stable. For system to be stable, the amplitude ratio has to be less than 1 corresponding to the crossover frequency. Clear? Now, on the same concept, your gain margin and phase margin works. Basically, if you're going to ask what is gain margin and phase margin, these are basically, the design parameters for designing of any controller, which includes the factor of safety. How, like if we are using proportional controller or PID controller, over there we have three parameters which are to be, optimized: KC, tau I, tau B. Now, all those parameters can be optimized using a standard factor of safety, and that factor of safety is basically your gain margin and phase margin. Clear? So let's first discuss about some few points about Bode stability, and then we approach towards what is gain margin and phase margin. I'll explain over here. Now, suppose we have a Bode plot and we have a phi plot. This is AR, this is phi. Let's say this is omega. And let's say this is the overall plot of AR and this is the overall plot of phi. Now, corresponding to a phi of minus 180, let me get a value of omega C naught. Now, corresponding to this omega C naught value, what is the value of AR? Let's say that value of AR comes out to be M. This is the first condition. Second condition is corresponding to AR of 1, I'll calculate some frequency, let's say omega dash, and corresponding to this omega dash, let me calculate some angle phi dash. Okay. So this means that for phi equal to minus 180, we have crossover frequency WC naught, and corresponding to this crossover frequency, we have an amplitude ratio which value comes out to be 1. So according to Bode stability, M should be less than 1 for system to be stable, and for unstable, M should be greater than 1. If the value of M is greater than 1, that means the system is unstable. And if the value of M is less than 1, so that means the system is stable. So from here, we define a very important term, that is gain margin. Gain margin is nothing but it's the reciprocal of AR. Gain margin is nothing but it's the reciprocal of AR. So in this case, so we have GM is nothing but 1 upon M. So according to Bode stability, for system to be stable, what should be GM value? GM should be greater than 1. And for unstable system, M will be greater than 1. So if M is greater than 1, so GM has to be less than 1. So either of the conditions are your Bode stability conditions. So this is where we define your gain margin. For gain margin, the system has for system to be stable, the gain margin value has to be greater than 1. If it is less than 1, that means the system is unstable. Now there are certain design specification parameters we can say typical specifications for designing purpose. For designing purpose, that means the gain margin value has to be greater than equal to 1.7. This 1.7 is basically a factor of safety parameter. Factor of safety parameter. So if gain margin is greater than 1 means the board is stability. The system is already a stable system. That's why we have taken a limiting value of 1.7. So this is the design specifications. That means if AR is, this also means that if AR can increase by a factor of 1.7 over a design value, the system becomes unstable. The system becomes unstable. Now a gain margin of unity or less than 1. Over here, if you look, if gain margin is less than 1, the system is always unstable. So if we include the factor of safety, the value of gain margin has to be taken a standard value, which is always equal to 1.7. 1.7 means whatever the parameters we will design, that already included the factor of safety parameter, and it can, and for a gain margin of 1.7, the system will always be a stable system. Also, you can also say higher the value of gain margin, higher the gain margin, more robust. Robust means well behaved. More robust the closed loop responses, or more stable the system is. More stable the system is. Clear? Also, in other words, we can also say higher the gain margin, higher is the factor of safety for controller tuning. Simple. जितना ज्यादा गेन मार्जिन होगा उतनी फैक्टर ऑफ सेफ्टी होगी ट्यूनिंग मतलब कंट्रोलर ट्यूनिंग करने के लिए. Second term which comes over here is your phase margin. Now what is phase margin? Let's see. Now for phase margin, if we look at the figure which is previously we have done over here, that is this thing. Now this difference is your phase margin. The phase margin is nothing but the difference between phase margin PM is nothing but 180 minus mod of 5. That's the phase margin. This is the phase margin. And for typically design specifications, the phase margin must be greater than 30 degrees. The phase margin must be greater than 30 degrees. If it is less than 30 degrees, we can say that the system is somewhat appearing to be unstable. So that's the designing parameter. So remember this, for design specifications, the gain margin has to be greater than 1.7 and phase margin has to be greater than 30 degrees. For a well-behaved tuning parameter, just remember this, for very well-behaved tuned controller, the gain margin can have a value between 1.7 to 4, and phase margin can have a value between 30 degrees to 45 degrees. So this is also one more important term, you can remember this. For a very well behaved tuned controller, मतलब इतना अच्छा ट्यून्ड होगा कि वो हर टाइप का एरर अकोमोडेट कर लेगा. अगर उसका गेन मार्जिन is lying between a range of 1.7 to 4 and its phase margin is lying between an error between a 30 degree to 45 degree. So in that case, the system will be a very well behaved controlled parameter, controlled tuned. Any doubt over here so far?
No, sir.
Okay. Now I'm gonna
margin.
हाँ बोलो.
जो गेन मार्जिन अगर 1.7 से कम होगा तो समवॉट अनस्टेबल होगा सिस्टम।
नहीं, स्टेबल तो बच्चे होगा, बिकॉज इट्स सेइंग दैट गेन मार्जिन इज शुड बी ग्रेटर देन 1। अगर बहुत अच्छा तरह ट्यून करना है हमने, तो वी नॉर्मली टेक इट टू बी इक्वल टू 1.7। 1.5 भी इट विल वर्क, 1.4 विल आल्सो वर्क, बट अगर 1.2 होगा, 1.1 होगा या 1 होगा, तो इट इज अपीयरिंग टू बी मोर टुवर्ड्स द अनस्टेबल साइड। तो एक स्टैंडर्ड डिफाइन है which says that it should be greater than 1.7। ओके, अभी एक्सप्लेन करूंगा अगर 1.7 हम लेते हैं तो क्या फर्क पड़ता है, और अगर 1.7 नहीं लेते तो क्या फर्क पड़ेगा। ठीक है, नाउ let's take the same problem which we took last time. I'll draw the problem over here. We have a controller system with KC, with final controlling element as 1, and a process with a lag of 1.5 and transfer function 1 over 0.5s plus 1 is the output. And it's a negative feedback word where the measuring element is also taken as 1. That's the R. Now for this particular system, we have already know its overall transfer function, which was Kc e minus 0.1s over 0.5s plus 1. And correspondingly, we determined as amplitude ratio, which was Kc over under root of 0.5 omega whole square plus 1, and correspondingly its phi was minus 5.79 omega minus tan inverse 0.5 omega. So these were the values which we determined in the previous class. Now for phi equal to minus 180, that means we equate phi equal to minus 180, and by using hit and trial we calculated its crossover frequency, which comes out to be 17 radians per minute. This we did last time. Now substituting this omega frequency in the amplitude ratio, so what we got was AR at omega c naught is equal to 0.12 kc. Yes or no? It comes out to be this value. Let's suppose this value is equal to M. Now we have defined what is gain margin. Gain margin is 1 upon M. That means it is 1 upon 0.12 kc. Now from design specifications, let's take gain margin equal to 1.7. So therefore, if gain margin is 1.7 and that is equal to 0.12 by Kc. So what is the value of Kc from here? So Kc comes out to be equivalent to, let's say, 4.9. Let's say Kc value is equal to 4.9. Clear? So I can use the value of Kc as 4.9 over here. Any doubt beta so far?
No sir.
Okay. So that means if I'm taking Kc as 4.9, and now this 4.9 has been calculated by considering the gain margin of 1.7. ठीक है, so that means design specification says अगर gain margin मैं 1.7 लेता हूं, तो उससे जो भी मेरा कंट्रोलर ट्यून होगा वो सिस्टम को स्टेबल ही रखेगा। लेट्स सी, so that means जो कंट्रोलर मेरा ट्यून हुआ, कंट्रोलर की ट्यूनिंग वैल्यू आई है 4.9। now let's see if it can stand an error. Now suppose in this process which is shown over here, the time for delay actual value of time for delay is let's say 0.15 instead of 0.1. Let's say because that is a human error for measuring the lag in a process. Instead of 0.1, the actual value is 0.15. Let's consider this an error in the system. So the actual overall, so the actual transfer function is Kc e minus 0.15s instead of this thing, instead of 0.1, it was actually 0.15. That is an error of 50%. An error of 50%. Let's consider an error of 50% in the system. Now, instead of 0.1, it was 0.15. So now the overall transfer function is this thing. Now, for what will be its amplitude ratio? Amplitude ratio remains the same. That is Kc upon 0.5 omega whole square plus 1. So there is no change in the amplitude ratio. But where does the effect comes? The phi changes. Now the phi will be minus 0.15 into 57.29 omega minus tan inverse 0.5 omega. Now let's calculate the now let us calculate phi equal to minus 180. What's the value of omega c naught? Substitute phi equal to minus 180 in this equation, equivalent to this equation, and calculate your crossover frequency. Now the crossover frequency comes out to be 11.6 radians per minute. Upon getting this value of 11.6, we're going to substitute in this value and find out AR. So AR is, now Kc we have already calculated. So value of Kc is 4.9 and 0.5 omega c naught whole square plus 1. We substitute the value of omega c naught and we calculate the amplitude ratio equal to 0.83. So what is the gain margin? Gain margin is 1 by AR. So how much is 1 by AR? How much is AR? So that is 0.8 inverse, which comes out to be 1.2. Now you can clearly see. Now gain margin is greater than 1. So according to Bode stability, it's greater than 1. So the system is still stable. The system is still stable. How? Initially, we have tuned the parameter by considering a gain margin of 1.7. Considering a gain margin of 1.7, we said that there is an error of 50% in the bed time. There is an error of 50%. कोई भी सिस्टम में अगर 50% एरर है और हमने गेन मार्जिन इक्वल टू 1.7 लेके उसको ट्यून किया हुआ है, will it be able to withstand that much error? ये चेक करना है. तो हमने गेन मार्जिन 1.7 करके हमने कंट्रोलर ट्यून किया, that comes out to be 4.9. Now we say that there is an error of 50% in the dead time. Instead of 0.1, it was actually 0.15. So what we do, we did the same analysis again. Now we wrote down the overall transfer function, the amplitude ratio, and the phase angle. Now we substituted phi equal to minus 180. We calculated the crossover frequency by hit and trial, and the crossover frequency comes out to be 11.6. Now we again substitute this crossover frequency in the amplitude ratio, and we already aware of the tuned parameter, which was equal to 4.9. So AR comes out to be 0.18. Again, it's less than 1 for system to be stable. So gain margin निकालिए दोबारा से, gain margin again comes out to be 1.2. Again system is stable. That means अगर मैं कोई भी कंट्रोलर गेन मार्जिन इक्वल टू 1.7 लेके ट्यून करता हूं, मिनिमम गेन मार्जिन ऑफ 1.7 लेके ट्यून करता हूं, तो it can withstand an error of 50%. It can withstand an error of 50%. Still, it can withstand an error of 50%, but 50% error बहुत ज़्यादा होता है. 50% error बहुत ज़्यादा होता है. So you can clearly see जो अब gain margin आया वो कितना आया 1.2. ठीक है? It is somewhat approaching towards 1. 50% error है, system still stable है, लेकिन now it is more towards your unstable side. It is more moving close towards the instability. समझ आया बेटा? अब doubt over here?
No, sir.
Now we can do the same thing again. Now if I take a gain margin of 4 over here, instead of your 1.7, if I take a gain margin of 4, I can tune this parameter again, do the same analysis. We can still see system stable होगा, ठीक है. So gain margin 1.7 ही minimum लेके हम system को tune करते हैं, and then we check whether वो system का error सिस्टम के एरर को वो स्टेबलाइज कर देगा कि नहीं करेगा, ठीक है. सो दिस इज व्हाट द ट्यूनिंग इज विद रिस्पेक्ट टू द gain margin. Now let's tune the system using phase margin. This was tuning based upon gain margin. Now we're going to tune the system using phase margin. For this, now we are already aware of we have phase margin and tuning. Now we already know that for the system, which is Kc1 and e raised to power minus 0.1s over 0.5s plus 1 Cr is a negative feedback. That's 1. Okay. So we know that the overall transfer function is Kc e minus 0.1s over 0.5s plus 1. We are aware that its amplitude ratio is Kc under root of 0.5 omega square plus 1, and phase angle is minus 5.9 omega minus tan inverse 0.5 omega. That's the phi. Now what is phase margin? Phase margin is nothing but 180 minus mod of phi. Now we know phi is this thing, so mod of phi will be the positive this thing. So phase margin comes out to be 180 plus 5.9 plus tan inverse 0.5 omega. Now for phase margin from design specifications, let's consider the minimum value of phase margin. For minimum value of phase margin should be 30. It should be in the range of 30 to 45 degrees. Should be in the range of 30 to 45. Now let's take phase margin of 30 degree. So if you take phase margin of 30 degree, so we can calculate the phi from, so we can calculate the omega. Let's say the omega comes out to be 12 radians per minute. Upon substituting this omega in this equation, so we can calculate your K. So AR is Kc 0.5 omega square plus 1. We substitute this value of omega over here and taking AR equal to 1, because why we are taking AR equal to 1? For phase margin, if you look at this figure over here, if you look at this figure, I've told you that if AR is 1, correspondingly we have some phi. So phase margin is basically the difference between 180 and phi. So in phase margin, we have to take AR equal to 1 for the tuning of the system. So for phase margin 30, we calculated the frequency, substituted in the AR equation and equating AR equal to 1. From here, we get Kc value as 6.08. So now we have tuned the parameters, that is Kc, which is 6.08 by considering a phase margin of 30 degree. Clear? So now let's again take the same error of 50%. That is, instead of 0.1s, the actual value of error was, the actual value of dead time was 0.15s over here. That is over here. Clear? So now so G overall will be nothing but Kc e minus 0.15s over 0.5s plus 1. its amplitude ratio will be Kc over under root of 0.5 omega square plus 1, and its phi will now be minus 0.15 into 57.29 omega minus tan inverse 0.5 omega. Now, what we have done is for AR equal to 1, and value of Kc equal to 6.08, for AR equal to 1, for AR and Kc 6.08, we're gonna calculate the value of omega. Let's say the omega value comes out to be 12 radians per minute. We're gonna find out the value of omega from here, which comes out to be 12 radians. Now we're gonna substitute this value of omega here and gonna find out phi. Now the phi comes out to be minus 184.76 this thing. So we can see that we notice that the system is still unstable, because if you see over here, minus 184, where does minus 184 lies? Minus 184 is lying somewhere here. It is lying somewhere here. It is lying somewhere here, minus 184. So it is greater than minus 180. It is greater than minus 180. That means whatever the controller we have tuned by considering phase margin of 30 degree, the system is still unstable. The system is still unstable. That means 30 degree margin लेके जो हमने system tune किया है, that is not withstanding the error of 50%. That is not able to withstand an error of 50%. Simple. Because जो phi आ रहा है, that phi is coming out to be minus 184.76. ठीक है? So now what we're gonna do is we're gonna again tune a parameter. Now by considering again a phase margin of, instead of 30 degree, now let's tune a parameter by considering, let's say 45 degrees. दोबारा ट्यून करके देखते हैं, फिर एरर चेक करते हैं, क्या पता अब जो ट्यून हुआ हो by considering phase margin of 45 सिस्टम स्टेबल होता है कि नहीं होता, बिकॉज 30 डिग्री पे जो हमने सिस्टम ट्यून किया था दैट इज 6.8, वो 50% एरर को विदस्टैंड नहीं कर पाया. दैट मींस 50% एरर और ये ट्यून्ड पैरामीटर सिस्टम को बचा नहीं पाया और सिस्टम मेरा अनस्टेबल निकला. ठीक है? सो नाउ वी गोना अगेन डू द सेम थिंग. Now again we're going to take phase margin of 45 degrees and find out, again going to tune a parameter. Now phase margin equal to 45 means 180 minus 5, and 45 degrees equal to 180 minus 5.79 omega minus tan inverse 0.5 omega mod. So यहाँ से omega आएगा 9.78. So if you put this 9.78 into this equation, 0.5 omega square plus 1, considering AR equal to 1, ठीक है? So यहाँ से तुम्हारे पास Kc की वैल्यू आएगी. Now the Kc value is 4.99. So we have a new tuned Kc which is 4.99. Now we're gonna check again with the same error. So controller tuned हो गया है by considering phase margin of 45. Now let's say an error of 50%. That is, instead of 0.15, it's actually 0.15. ठीक है? So overall transfer function was Kc e minus 0.15s over 0.5s plus 1. ठीक है? और इसका एम्पलीट्यूड रेशियो कितना है? Kc अपॉन अंडर रूट ऑफ 0.5 ओमेगा स्क्वायर प्लस 1, और इसका पाई कितना है? माइनस 0.15 इंटू 57.29 ओमेगा माइनस tan इनवर्स 0.5 ओमेगा. ठीक है? ये सिस्टम है. नाउ Kc कितना है? 4.99. AR को इक्वल टू 1 सब्स्टिट्यूट किया. सो यहां से आई विल फाइंड आउट माय omega. Let's say the omega comes out to be, omega निकालेंगे हम यहाँ से, ठीक है, ओमेगा आएगा तुम्हारे पास कितना, लेट्स सी कितना आता है ओमेगा, 4.9 का, फाइंड आउट द वैल्यू ऑफ ओमेगा. Yeah, omega comes out to be 9.78. So omega 9.78 आया. Substitute that omega over here in this expression and calculate your phi. Now the phi comes out to be minus 163.38, which is where it is lying. It is lying somewhere. If you see minus 163, it is lying somewhere here. It is lying somewhere here. Minus 163 degree. Clear? So that means अगर मैं कंट्रोलर ट्यून करता हूं by considering a phase margin of 45 degrees, so 45 डिग्री पे मेरा जो सिस्टम है वो स्टेबल आता है because this value is in a range of 5 between 5 and minus 180. Clear? So this is how we tune a system using gain margin and phase margin. So the overall summary of this topic was, अगर gain margin मैं 1.7 लेके कंट्रोलर ट्यून्ड करता हूं, सो जो भी उसकी वैल्यू आएगी दैट कैन विथस्टैंड एन एरर ऑफ 50%. वेयर एज फेस मार्जिन अगर मैं 30% लेके 30 डिग्रीज लेके कंट्रोलर ट्यून करता हूं, दैट इज नॉट एबल टू विथस्टैंड एन एरर ऑफ 50%. बट अगर मैं फेस मार्जिन 45 डिग्रीज लेके सिस्टम ट्यून करता हूं, इट इज आल्सो एबल टू विथस्टैंड एन एरर ऑफ 50%. So remember this, for a very well behaved controller tuned, the gain margin should be in a range of 1.7 to 4 and phase margin should be in a range of 30 degree to 45 degrees. So you can take normally the minimum value of gain margin and phase margin will be given to you for tuning a controller. Suppose question area, tune a controller by considering a gain margin of 2.8 and verify whether the given tuned parameter is able to withstand an error of 50% or not. Okay, so you have to work in a similar basis. So for a well behaved, these are the typically designed specs. Otherwise, remember this thing, for Bode stability, the gain margin has to be greater than 1 for a system to be stable, and or AR has to be less than 1 for a system to be stable. अगर gain margin 1 से कम है, system unstable है, और अगर AR 1 से बड़ा है तो system is unstable. ठीक है? So this is where your phase margin is, gain margin and phase margin is over. So we are left with now only two topics. One is Nyquist plots and the last one is your controller tuning. Okay, so we're gonna discuss about those in the coming lectures.